Hi, I'm Aaron Sampson, and I've been a professional in the IT industry since 1995. With a primary focus on technical training, I can be found most of the time producing and delivering learning content centered around network infrastructure and services. I've also been involved with extensive practical implementations in a variety of operational capacities, including architecture and design, deployment and implementation, administration and management, and various other technology-based roles. Every computer requires a storage device and random access memory, or RAM, but both are available in many different varieties and configurations. In this course, I'll begin by exploring virtual RAM and the small outline dual inline memory module, more commonly known as the SODIMM. From there, I'll explore double data rate, or DDR RAM, and the features of memory channels. Next, I'll cover the features of solid-state drives, or SSDs, and magnetic hard drives, and compare and contrast features of the two most common physical sizes for hard drives, 3.5-inch and 2.5-inch. I'll also explore removable storage options and their benefits, and learn the differences between the various levels of a storage solution known as RAID, or Redundant Array of Independent Disks. This course will help to prepare learners for the CompTIA A Core 1 or 220-1101 certification exam. In our first video for this course, we'll examine the use of what's known as virtual memory, whereby any given computer can gain access to additional memory without adding any physical RAM. Now, that immediately raises the question, where does this additional memory come from? Well, it actually comes from the computer's primary storage device, or the hard drive, but we'll get into that in greater detail in just a moment. But to just quickly address the term simulates in this graphic, that's kind of correct, yet incorrect at the same time. To clarify, the computer does have access to more memory than what is physically installed in terms of RAM, so it's real in that regard. But a computer's processor only ever works with data that is actually in memory at any given moment. In other words, if the processor calls for data that is not in memory at that particular moment, it has to be retrieved back into memory. So that's where the simulated aspect comes into play. You are providing the ability to store more data in memory, but for lack of a better word, it's not stored in active memory. Now, again, this will all be fleshed out in greater detail in just a moment. So, in terms of implementation, virtual memory is useful in any situation where the amount of actual RAM in your computer is insufficient, and the process itself is managed by using both hardware and software. The hardware component is your hard drive and, in fact, your processor, but the software component is effectively your operating system, which manages the overall process automatically. So, as mentioned, virtual memory utilizes free space on your hard drive to act as additional memory. But there are some considerations in that regard, and we'll get into that in greater detail in just a moment as well. So, why is it even used in the first place? Well, quite simply, modern operating systems do require a lot of memory. But I should qualify that the term modern is being used somewhat loosely here. The use of virtual memory has been around at least since I began my career as an IT professional, which was in 1995. So it's not all that new. But in addition to the requirements of the operating system, of course, the applications that we run are also becoming much more demanding, and we tend to want to run more of them at the same time. In which case, there simply might not be enough actual memory to support that kind of workload. Now, before going any further, of course, the physical amount of RAM that is inherently present in any given computer has, of course, been increasing over the years as well. And just to give you a quick idea as to how much it has increased, when the first computer appeared in my house, it had 4 megabytes of RAM. The laptop I'm using right now, which is already about 3 years old, has 16 gigabytes. That's 4,000 times as much memory. So clearly we have access to much more RAM these days. But of course the operating system and the applications are far more robust as well. So it's really a never-ending battle. The more advanced we want our software to be, the more memory we require. And the more memory we have, the more demanding new applications will become. All told, running out of memory is in fact far less of an issue these days, but virtual memory is still in use today, even with the comparatively vast amounts of memory we have at our disposal. So with that all said, let's take a look at the process. For starters, all memory in your system is broken down into smaller addressable units. And a good way to think of that is to imagine post office boxes on the wall of something like an apartment building. All information comes into the building in the form of mail, but of course, some of it's for me, some of it's for you, and some for everyone else. So the addresses on each post office box allow each of us to locate the appropriate information. So these addresses will be applied to all of your physical RAM, but also to a dedicated portion of the hard drive. But your system will maintain the distinction between physical and virtual addresses in a hardware component of the CPU referred to as the Memory Management Unit, or MMU. So the system will monitor how much information has been addressed into the physical addresses of actual RAM, but even if there is enough RAM to accommodate all of the information in all addresses, in most cases, there is data in any given address that has either not been used recently or is not being accessed frequently. That unneeded data, if you will, is then identified and moved to virtual addresses on the hard disk, which has the immediate result of freeing up more actual RAM, which is essentially always a good thing. In simple terms, your system likes having a lot of free RAM. Now, as mentioned, the so-called unneeded data is simply moved to a specific location on the hard drive that has also been addressed. So your system knows exactly where it is, and that collection of addresses on the hard drive is in fact referred to as the swap file or the page file, so that if and or when the data is needed again, it can be located very quickly and returned to actual memory. And that process itself of moving the data back and forth is referred to as swapping or paging, which is where the file gets its name. Now that all said, the process does still involve moving data from one place to another. So it's not as fast as actual RAM, but again, it gives your processor access to more addresses overall and therefore more data. And it gives priority to the most frequently accessed data while keeping the less frequently accessed data on standby, if you will. And although I've been using the term hard drive thus far, I really should have just been saying storage device, because many systems these days have solid-state drives, which significantly outperform their hard drive counterparts, and therefore they can significantly increase the speed of paging or swapping that data to and from memory. Now, all processes involved with virtual memory are managed by default on most systems. But as an example, if you're running a Windows platform, you do have the option to control some of its configuration to a degree. The system will still decide which data is going to be swapped and which data won't, but you can specify a few parameters with respect to where the page file is stored, if in fact you want to create multiple page files, and the minimum and or maximum size for the file or files, or even disable it entirely, which is generally not recommended unless you're certain that you have more than adequate memory for all situations and that disabling it won't adversely affect performance. The default state for all versions of Windows, though, is for virtual memory to be enabled and for it to be entirely managed by Windows itself. So to finish up, like anything, there are pros and cons. So on the plus side, the use of virtual memory can improve overall system performance, as well as the ability to run many applications at the same time, or to run very memory-intensive applications more easily. On the downside, the process is certainly slower than physical RAM, and the page file itself in some cases can be fairly large. So if you're running low on disk space, this would have to be monitored closely. And on that note, the typical size is often initially calculated by the amount of memory that you actually have, which in the past was around 1.5 times the amount of RAM. So if you had 4 gigabytes of RAM, the page file would be 6 gigabytes. But in recent times, the amount of actual RAM has gone up so high that a page file that large would almost never be allocated. And if you're relying on virtual memory too much, it can lead to excessive paging, which simply slows the process even more. And if you do decide to configure it manually, an incorrect configuration could lead to even worse performance or even boot failures. So in most cases, the recommended approach is to let the operating system manage the process entirely. One final note, if you do notice that your system is paging too much, you can certainly check the configuration to see if perhaps the file was set too small, and you could increase it as long as disk space isn't an issue. But that really should be regarded as a temporary fix. Excessive paging is an indication that your system simply does not have enough actual RAM. So the solution is not really to allocate more virtual memory, it's to get more RAM. In this presentation, we'll take a look at the small outline dual inline memory module, more commonly referred to as the SODIMM, which is the physical form factor for the memory chips commonly found in laptop computers, hence the small outline part of their name. They are generally about 40 to 50% smaller than their desktop counterparts due to the limited space in most laptops. But in terms of performance specifications, they're pretty much on par with standard dual inline memory modules. Now, the dimensions of any given SODIMM will usually be fairly consistent across various makes and models, but all types of memory chips have a notch along the bottom where the pins are, which ensures that the chip is inserted in the proper orientation. But the placement of that notch itself can vary depending on the model. So if you're considering an upgrade or a replacement, it's probably best to take an existing module with you as a reference, particularly with respect to ensuring that you get a compatible module with respect to its speed and pin configuration, which we'll cover in greater detail in just a moment. But in general, memory modules are fairly easy to upgrade or replace, but that will also depend on the model of the laptop itself. Some may provide easier access to memory than others. So coming back to the speed, in fact, we'll cover each of these in greater detail in some upcoming videos as well, but SODIMMs are available in the same speeds as standard memory modules, and they employ the same double data rate or DDR technology. Now, for starters, the double aspect of double data rate must have a single data rate that it uses as a reference, and in fact, that is exactly the case. But in this context, it doesn't refer so much to doubling any particular speed. Rather, it doubles the amount of information transferred on each cycle. Data is moved in and out of memory using cyclical electrical pulses. So single data rate only transfer data once per cycle, whereas DDR uses more tightly controlled timing to recognize both the rising and falling edges of the clock cycle to transfer data twice per cycle in a process known as double pumping. Now, from that point, of course, like all computing technologies, DDR itself has also been improving ever since, with DDR releases advancing through DDR2, DDR3, DDR4, and at the time of this recording, its latest revision of DDR5. Again, each of these will be covered in greater detail in some upcoming videos, but suffice to say that each revision improved upon the performance of its predecessor. But again, SODIMMs, despite their smaller size, still adhere to all DDR specifications. So just to give you a better idea of the more current specifications of DDR5, it was released in 2020, and supports a maximum single DIMM size of 128 gigabytes, which quadrupled its predecessor. Now, just a quick note on that value. If you're searching around a bit, you might see a maximum value of 256 gigabytes, but that would refer to the fact that almost all DDR implementations use two channels or two physical sockets. So to take advantage of dual channel memory, you have to use two modules. So for all practical purposes, while a single DIMM chip itself might only have a maximum size of 128 gigabytes, if your system requires two chips, then of course the maximum becomes 256. It uses a lower 1.1 voltage, which is also lower than all previous DDR implementations, which helps to reduce heat, which of course is beneficial in the more limited space of a laptop, and in its highest performance configuration, it supports an eye-opening bandwidth of 51.2 gigabytes per second. And do take note of the uppercase B. This is in fact gigabytes per second. Translated into gigabits, that's just shy of 410, which is approaching half a terabit per second. Now, that all said, while this may have some people scrambling for the latest and greatest for their laptops, at the time of this recording, SODIMM DDR5 chips are just starting to hit the market, mostly in Japan. And even if you could find the chips themselves, it would be quite unlikely that you would find an existing laptop that supports DDR5. So save your money for now. But again, like all advances in technology, it likely won't be long before this becomes the standard for new devices. In this video, we'll examine some of the performance characteristics of double data rate or DDR3 memory. Now, in short, we're starting with revision 3 of DDR simply because DDR2 was released back in 2006, so over 16 years ago at the time of this recording, so it can largely be considered as a legacy version. That said, even DDR3 itself was released over 10 years ago, but it wouldn't be surprising to still see DDR in some older systems. But as you might expect, in its highest performing release, DDR3 doubled the speed of DDR2 in terms of overall bandwidth, and was most commonly available in a 240-pin DIMM or dual inline memory module configuration, and a 204-pin SODIMM or small outline dual inline memory module configuration. And like DDR2 was to the original DDR, all implementations of DDR3 are incompatible with DDR2. Now, with respect to its performance characteristics, the values that are used as benchmarks for performance are the same across all implementations of DDR, but of course it's the values themselves that are increasing. But among those primary benchmarks are the bus clock speed, which can be thought of as the communication channel between the memory chip itself and the processor, which for DDR3 ranged from 400 to 1066 megahertz. But the chip itself could handle 4 cycles per bus cycle. In other words, when it comes to all implementations of DDR, there are actually 2 applicable clock speeds, the speed of the bus and the speed of the chip itself. And because the chip does not really have to be concerned with anything else that might be going on within the system, chip speeds are invariably faster than bus speeds. So to help visualize the relationship, just imagine an actual bus stop. The bus comes along at regular time intervals to transport people to a particular location. That's the bus speed. But in this particular case, instead of just picking up one person at the bus stop, 4 people have gathered, and all of them can get on the bus at the same time. So, in short, the data being processed through the chip is just very briefly cached, if you will, like people waiting at the bus stop, until the next bus cycle, at which point more data can be sent for processing. As is the case with all DDR memory, DDR3 continues to transfer data twice per clock cycle. Again, this is a process referred to as double pumping, whereby data is transferred on both the rising and the falling edges of the cycle, which is effectively the double in the term double data rate. And all of this resulted in a bandwidth ranging from 6,400 to 17,066 megabytes per second. As for the physical chip itself, in its DIMM form, really the main characteristic is the notch along the bottom where the contact pins are. Again, this is to ensure that the chip is inserted in the correct orientation, but that notch is almost always slightly off-center, and also not in the same place as DDR2 chips, which prevents mixing of the two types. And finally, another value that indicates the performance level of the module is what's known as the MTS value, which stands for million transfers per second. And you'll often see this included in the name when referring to the chip. For example, DDR3 1600 means an MTS value of 1600. And this also was twice that of DDR2. So again, the higher the value, the better the performance. So, of course, as consumers, we would always want the fastest speeds that could be supported by our systems, but like anything, the higher the performance level, the higher the cost. In this presentation, we'll take a look at what is likely the most common form of double data rate or DDR memory in use at the time of this recording, which is DDR4. Now, this is available in both DIMM and SODIMM form factors, and like DDR3 doubled the overall bandwidth of DDR2, DDR4 does the same and doubles that of DDR3. The DIMM implementation used 288 pins and 256 for the SODIMM, which again, like all previous implementations of DDR, means that DDR4 is also incompatible with all earlier versions. As for the specific performance values, DDR4 ran on a bus clock speed between 1066 and 2133 megahertz, and 1066 megahertz, by the way, is exactly where DDR3 came in at its highest level, so 4 picked up right where 3 left off, and its overall bandwidth ranges from 12,800 to 25,600 megabytes per second, and has an MTS or million transfers per second range of 1600 to 3200, which, like DDR3, is often expressed in the name. So a DDR4 3200 chip refers to the MTS value. Once again, the notch along the bottom edge of the chip itself determines the orientation when physically inserting it into its slot. And like its predecessor, DDR4 also has the notch slightly off-center as well, but on the opposite side from DDR3 if compared in the same orientation. So again, DDR4 is not compatible with any of the previous versions, and the chips cannot be mixed and matched. Now, I mentioned at the start of this video that DDR4 is likely the most common type of memory in use at the time of this recording, but it has also reached its end in terms of further development. In fact, for all versions of DDR since the original release, the lifespan of each version has been around 4 years, and DDR was released in 2016. So development effectively stopped in 2020. So while it is still probably the most common, DDR5 has been released and is expected to continue its development into or around 2025. And we'll discuss its characteristics in the very next video, but for now, DDR4 won't be seeing any further improvements. And while the specifications for DDR5 have been released and the chips themselves are available, it is very new on the market, and there may not even be any systems that support it yet, but it is on the way. In the meantime, DDR4 will certainly continue to perform very well in any system that supports it. In this video, we'll examine the performance characteristics of DDR5 memory, which was introduced in 2020 and promises to be the standard for memory modules through 2025. And of course, as you might expect, all of its performance values exceed that of its predecessor, despite the fact that it actually consumes less power than all previous DDR implementations. But for most of us, of course, the speed is the main concern. Also, like other versions of DDR, version 5 doubles that of version 4. In terms of specifics, the lower voltage comes in at 1.1 volts, whereas DDR4 operated at 1.2. Now, that's not all that much of a difference, but in devices such as laptops, lower power consumption means longer battery life and less heat produced. In fact, DDR5 is also expected to incorporate its own onboard voltage regulators in order to reach even higher speeds when needed, although that will come at an additional cost, and it's expected to be more of a network server feature or perhaps a high-end specialized workstation feature. In other words, you typically would not see it on standard desktops or laptops. But as mentioned, for most of us, the important number is the bandwidth, and once again, DDR5 doubles that of its predecessor with an impressive overall bandwidth of 51.2 gigabytes per second and a million transfers per second, or MTS range, from 3200 to 6400, again doubling that of DDR4. In terms of the capacity for any single module, it quadruples its predecessor, supporting up to 128 gigabytes. But again, recall that this value is for a single DIMM, and almost all DDR implementations require two modules in a dual-channel configuration. So in that regard, the practical maximum value for a dual-channel system is 256 gigabytes. But DDR5 is also being developed to support a new architecture known as die stacking. And the dies refer to the actual individual chips on the module itself. And this allows multiple dies to literally be stacked onto a single module in a configuration known as load-reduced or LRDIMM, which should provide support for an incredible 4 terabytes capacity on a single module. But that has yet to actually be implemented. So just to finish up, given that we've discussed several different types of DDR modules, I'd like to just reiterate that no version of DDR is compatible with any other version. And the specifications notwithstanding, it really does come down to the fact that the small notch along the base of the module is located differently on each type, and possibly even with a different size. So even if there's no label, you simply can't install the wrong version of DDR memory into a system that wasn't designed to support that version. So if your system is currently using the highest capacity modules with the fastest specifications of something like DDR4, then your only option for upgrading is to get more modules. But even then, you can only do so if there are still available slots. So if all slots are full, then you have no option to upgrade the memory of that system any further. You'll have to upgrade to a new computer, or at least to a new motherboard that supports DDR5. But just to put that into perspective, if your system has, let's say, 4 physical slots, and they're all full with the latest and greatest DDR4 modules, then you're currently running at 128 gigabytes of RAM. So it would be hard to imagine that an upgrade would be particularly required. In this presentation, we'll take a look at a feature of memory known as error checking and correcting, or ECC memory, which provides a mechanism for discovering and correcting single-bit memory errors, which refers to an issue that may occur when any given bit out of any given byte of memory encounters an error while being written or read, making it more reliable than non-ECC memory because it can quite literally correct errors. But this does come at the price of requiring more processing, which in turn translates into ECC memory being a little bit slower. But depending on the application, that's not necessarily a bad thing. On that note, the use of ECC memory essentially comes down to data integrity versus processing speed. In short, if the only concern is speed and more of it, there can be more errors that might go unnoticed. Think about any job. The faster you do it, the more likely you are to miss something. But if you slow down, while the job might take longer, you'll likely end up with a better result. So in some applications, accuracy and integrity are more important than speed. In terms of the physical chip itself, ECC memory can be identified because on a standard memory module, there are 8 actual chips that effectively handle the data. Now, in this graphic, we're just focusing on those memory storage chips. There would be more than just those. But on an ECC module, there is a 9th chip, making the two types easily distinguishable from each other. So that 9th chip is implemented to perform what's known as parity, which refers to a process whereby for every 8 bits written, a 9th bit is also stored, which is why there are 9 modules on the chip. It provides a means to store the extra bit. So parity works by examining each byte written, which is of course 8 bits, and then the total number of ones are summed up. Now, with only 1 extra bit to store the parity information, the value of the summed up ones is stored only as either an even number or an odd number. So, as an example, if there were 4 ones written in that byte, then the 9th bit is set to 0 to indicate what's known as even parity. If there were 5 ones in the byte, then the 9th bit is set to 1 to indicate odd parity. Now, that in itself doesn't provide any error correction, but when that same data is read, the byte that is read is then compared against the parity value. So using our first example of even parity, when the data is read, if the number of ones read produces an even number, and the parity bit is set to even, then that data is assumed to be correct. But of course, the opposite then is also true, in that if an odd value is produced, but the parity bit indicates that it should be even, then the values don't match, and the data is then assumed to be corrupt. So error-correcting memory will attempt to repair that byte by using algorithms that were generated when the data was originally written to identify which bit is in error, and it will attempt to correct it by simply changing the bit value from 1 to 0, or vice versa. Now that said, this process is limited to single-bit errors within each byte. So going back to the earlier example, if 4 ones were written, then the parity bit will be set to 0. So far, so good. But then, if that byte is read and 6 ones are read, well, that's still an even number. So with the parity bit set to 0, the system would assume that data is correct. So in other words, the error-correcting process cannot correct 2-bit errors. But the chance of 2 bits being corrupt as opposed to just 1 is of course much less likely. But given that, ECC does tend to be less common in modern systems simply because the reliability of the hardware itself has increased, as have other methods of implementing data integrity checks, such as improvements to the protocols for writing and reading data. So although ECC memory is still considered to be more reliable, modern technology has simply reduced the need for it. So I would say that it might only be found in systems that are considered to be a little more mission critical, or those that are designed for a specific task. Most standard systems, for lack of a better word, would not have ECC memory installed by default, although just about any system could have it installed. In this presentation, we'll talk about what's known as single-channel RAM, which refers to the communication channel between the system memory and the CPU, which is also known as the system or the memory bus. Now, data ultimately flows between the processor and your RAM via this pathway, and in most modern systems, a single physical RAM chip operates over a 64-bit channel. So to imagine that, just think of that entire channel as a highway that, in this case, has 64 lanes. So clearly, the more lanes there are, the more information that can be supported on that channel. But since all data moves over that bus, if your system only has a single channel, but two physical memory modules installed, then they have to share that channel. Now that's perfectly fine, but if your system has only that one channel, again with two physical chips, they are sharing the channel, but it simply means that a little bit of timing has to be implemented so that data retrieved from one chip doesn't try to access the bus at exactly the same time as data retrieved from the other. So looking at an example of that, in this graphic we see two slots for two physical chips, DIMM1 and DIMM2, but they're both operating on channel A. Now the slots themselves could be just about any color. In this example we see red and black, and that's perfectly fine, but you might see the same color for both, such as black or red, or again, really just about any other color. So don't get too hung up on what color yours might be or what you might see in any pictures. It's the channel labeling that matters. So if you only see a single channel, such as channel A, then those two physical chips are going to be sharing that channel. Now, the bus itself is collectively made up of three sort of sub-pathways, if you will. So coming back to my highway analogy, some lanes of that highway would be designated for certain types of traffic, such as when you see a carpool-only lane. So for the memory bus, those sub-pathways include the data bus, which carries the actual data, the control bus, which handles how that data is moved, for example, managing the timing that I mentioned earlier for when two modules share the same bus, and lastly, the address bus, which manages the locations for where any given data might reside in memory for when it has to be read from or written to the bus. So again, all of that information, the data, the control, and the address are just subcomponents of everything that's traveling back and forth. And just to come back to the highway analogy for just a moment, this all still applies to an actual highway. The data would represent the vehicles traveling on the highway. The control would represent things like the speed limit over different sections or the number and or the direction of the highway. And the address would represent something like the exit signs that direct us when and where we can exit or enter the highway. So again, regardless of the number of physical chips, all chips must share that single channel, which does involve a little more processing with respect to timing because, again, data from two different addresses on two different chips cannot both access the bus at exactly the same time. But all memory across all chips is still addressed separately. In other words, physical chip 1 does not use the same addressing scheme as physical chip 2. All memory is seen as a single address space, so most of the time, any given amount of data that has to be retrieved or accessed will be within the address space of a single chip, which inherently helps to reduce the amount of times that data has to be retrieved from both chips. But again, even when that does happen, it only requires a little bit of time and processing to ensure that they each access the bus separately, so the overall impact on performance is minimal. Now, all of that said, there is one advantage to having single-channel RAM in that it supports the use of only one physical chip, which can result in a little bit of cost savings. But if you're using dual-channel RAM, which we'll see in our next presentation, in order to take advantage of the dual-channel architecture and its benefits, you have to use two physical chips, which of course would increase your cost as opposed to having to only buy one chip. But that said, of course, it would also increase your overall memory capacity. In this video, we'll take a look at dual-channel RAM, which, as its name indicates, implements two separate dedicated memory buses of 64 bits each. So, as opposed to single-channel RAM, whereby if you have two physical chips, they both share the same channel, clearly with dual-channel RAM, each chip gets its own channel. So if there are only two physical chips, each one now has a dedicated channel to use, which eliminates the timing issue of using a shared channel. Now, that said, there can still be a similar configuration to single-channel RAM, in that if you have four physical chips, then two chips will operate in pairs, and each pair will still share their respective channel, but you still have twice as many channels to use. So in terms of implementation, a typical dual-channel motherboard will have at least two, but often four physical slots. So let's just imagine for a moment that we have a single DIMM chip, call it DIMM 1, in channel A. That configuration all by itself would work just fine. But as it is, you would only be operating over a single channel. So then if you purchase a second physical chip, call it DIMM 2, and you installed it into the other slot of channel A, then what you are effectively doing is defeating dual channel RAM because you've got both chips in the same channel. So you're effectively downgrading your system, if you will, to single channel RAM. Now, while that would work, those two chips are now sharing just the one channel. So for situations where you do have two physical chips, one should be placed in channel A and the other should be placed in channel B, so that each has its own dedicated channel, eliminating any timing issues and offering better performance overall. Now, if you have four physical chips and four physical slots, then simply install each chip into each slot, and there would be no concern for which chips are where. This will still be beneficial in that you will increase the overall memory capacity of your system, but you will once again have two chips that are sharing the same channel. But since there are still two dedicated channels as opposed to one, this still offers better performance. The only thing I might suggest in terms of maintaining the best performance would be to still go with just two chips. But if you were looking for the higher capacity overall, then each chip would have to be twice as large. In other words, two chips of, let's say, 8 gigabytes each would perform a little bit better than four chips of 4 gigabytes each. In either case, you still have 16 gigabytes of RAM in total, but those higher capacity chips would likely be more expensive. And I should also mention that the capacity of paired chips does not necessarily have to match. The specifications in terms of speed and throughput typically do, but if, for example, your system originally came with 4 gigabytes of RAM in two chips of 2 gigabytes each, you might be able to upgrade by installing two more chips of 4 gigabytes each for a total of 12. But in that case, I would recommend that you keep the original chips in channel A and the new chips in channel B for consistency. Now, to quickly clarify, I say might in this case because the ability to use different capacity chips isn't necessarily prohibited by the architecture itself, but it may be prohibited by the manufacturer of that particular motherboard. So I would suggest that you consult the documentation before making any new purchases, and ideally it's always just best to keep everything consistent anyway. Lastly, regardless of the number of physical chips, all available memory is still addressed as a single address space, so there are no conflicts when retrieving or accessing data in memory, regardless of which chip might actually store the data. And because there are now two dedicated channels, operations can be performed simultaneously over each channel. Plus, the overall bus width is increased from 64 to 128 bits, which translates into improved performance across the board, but particularly with respect to being able to multitask access to your memory. Both channels can be used at the same time, and each one is as wide as it is in single-channel RAM. In this video, we'll examine triple-channel RAM, which of course is the next iteration with respect to implementing multiple channels for your system memory. Now, as its name indicates, triple-channel RAM implements three separate dedicated buses of 64 bits each. So now, if you have three physical chips, then each one can still have its own channel. Now again, depending on the motherboard, there may still be slots for two physical DIMMs on each channel, which is fine because with that configuration, you can support as many as 6 physical chips. But just like in dual-channel RAM, each pair of DIMMs can still share one channel, but there are still separate channels for each of those three pairs. So, just as with dual channel RAM, it simply comes down to how many physical chips you have versus how many slots. So, if you have 3, then to take advantage of triple channel architecture, then each one should be placed in each channel. If you have 6 chips, then simply fill every channel, and again, each pair will share its own channel, but that's fine. So with triple channel memory, the bus width increases to 192 bits. So once again, we have a wider highway, if you will, capable of supporting more traffic. And when using triple channel RAM, again, if there are only 3 physical chips, then each one operates on its own dedicated channel when communicating with the processor, and they can all be accessed simultaneously. But be sure that if you do have 3 chips, that each chip is placed into its own dedicated channel. In other words, you wouldn't want 2 chips in channel A, 1 chip in channel B, and then channel C left empty. This would still work, but once again, it would defeat the purpose of having 3 channels. Now, I should also mention that although you might have the ability to support triple channel RAM, you need to be mindful of the total number of chips versus the total number of slots. For example, you might have only 4 physical chips, but 6 slots, in which case you could just put 1 chip in each slot, which would give you triple channel RAM. Then you could install the 4th chip into any other channel, and that particular channel would be shared. But I would suggest that if 4 chips are going to be used, that they should be configured so that you only use 2 channels, effectively using it as a dual channel system, and just leave the 3rd channel empty, because there would be less of a timing issue if data is only being transferred over 2 channels as opposed to 3. And there would be a little more management involved with respect to addressing, because the address space of the channel with 2 chips would be larger than the other 2 channels with only 1 chip. This also leaves that 3rd channel entirely free if you decide to upgrade later on. You could just buy 2 more chips to populate that remaining channel. In short, if you have triple channel RAM with 3 slots, then simply fill each slot. If there are 6 slots, then use either 3 chips with 1 in each channel, or use all 6. In this presentation, we'll discuss the next iteration of multi-channel RAM, which is quad channel, and of course its name pretty much tells the story in that there are now 4 memory channels, which of course can support at least 4 memory modules, with each one still having its own dedicated channel. Now, just like triple channel and double channel, ideally all 4 memory modules should be placed in their own channel to take full advantage of the architecture. But one thing to note is that quad channel architecture does require identical chips in terms of the performance specifications and the capacity, which differs from dual channel, where you may be able to mix modules of different capacities, but even then it would be dependent on the motherboard manufacturer. This is probably the case with triple channel RAM as well, in that you should have the same specifications and the same capacity. Now, if you have less or more than 4 chips, then you should still make use of separate channels. For example, if you only have 2 modules, one should be placed in channel A and one in channel B, and it will operate in dual channel mode. If you have 3 modules, then place one in each of channels A, B, and C, and it will operate in triple channel mode. So then, of course, if you have exactly 4, then place one in each channel as opposed to 2 chips in channel A and 2 in channel B. Now, if you happen to have 8 slots, then still follow the same pattern. In other words, if you have 6 chips, then install 2 in each of channels A, B, and C. And once again, it will operate in triple channel mode. And if there are 8 chips, then simply fill all 8 slots. Ultimately, like earlier architectures, the number of channels being used is dependent on how many modules are actually installed. For instance, if you go all the way down to just using a single module, which would work, then the system will only operate in single channel mode. 2 modules in 2 channels gets you dual channel mode. But it is worth mentioning that when dealing with quad-channel systems, it could be the case that using 3 modules in 3 channels may not be supported. It will depend on the specific type of system you are working with, but in some cases, you might find that quad-channel might only support doubling the channel values. In other words, going from single channel to double channel, then double channel to quad channel, essentially skipping over triple. But again, before making any purchases, simply check with the documentation. But any channel left empty will of course mean that you won't be using all 4 channels. Or to put that another way, the number of modules used in their own dedicated channels will determine how many channels are actually being used. Lastly, in terms of pros and cons, there are mostly pros in that overall system performance will be increased, as in a quad-channel system, the memory bus is now 256 bits wide, which of course is 4 times that of single-channel RAM, and it will likely support a higher overall capacity, but that would still be dependent on the total number of slots. But 8 are supported in a quad-channel architecture, so the only downside really would be the cost of possibly having to purchase up to 8 modules if you want the highest level of capacity. But typically such systems are used for dedicated or very demanding tasks, so the performance gain is usually worth the extra cost. In this presentation, we'll take a look at hard disk drives, which implement electromechanical data storage, which is quite simply a reference to the fact that they have moving parts, including rapidly rotating magnetic platters and an actuator arm that moves back and forth across the surface of the disk while it spins. At the tip of that arm is a read-write head that applies an electrical charge to write data and senses that charge when reading data. In terms of structure, most drives will actually have 2 physical platters on a single spindle, spaced about a centimeter apart, and each platter has 2 surfaces. So in a 2-platter drive, there would be 4 surfaces in total, so there would also be 4 read-write heads on the actuator arm. Now, when data is being written, the operating system will always attempt to find continuous space on the drive, but of course any given file could have been written at any given time in any given location. So accessing existing data is done randomly, meaning that the data has to spin to the correct location and the read-write head has to be moved to the correct location as well. So when compared to something like a solid-state drive, they will simply never reach the same level of performance due to those moving parts. But for a very long time, traditional hard drives have provided a reliable and comparatively inexpensive means to store non-volatile data, meaning that power is not required to retain the data. The cost of the type of non-volatile memory that's used in solid-state drives has only recently come down enough in price to make them a viable choice for long-term storage. As for some of the key characteristics, standard hard drives have been around for decades, so it's a very mature technology which translates into high reliability. For example, I have an external hard drive on my desk right now that I've had for at least 10 years, I'm thinking possibly 12, and I've never had a single issue with it at all. But I should mention that due to those moving parts, they are somewhat susceptible to mechanical failure, but of course that's true for a lot of things. But with respect to the storage aspect itself, in many cases you can expect as much as 20 or 25 years worth of reliable data storage on a unit that is well maintained, by which time it's highly likely that the data would have been moved to a newer device anyway, so it's not uncommon for the device to outlive its usefulness, so to speak. They're also very cost effective, although the price of solid-state drives has certainly come down, but you usually get a much higher capacity for more or less the same price. So on a per gigabyte basis, hard drives would still be less expensive, and in terms of the interface, most units these days would likely be using serial ATA, but it certainly wouldn't be out of the question to still find some older IDE interfaces, and you would also likely find the SCSI interface if you're working with drives in network servers. In terms of performance, there are several factors that will dictate the overall throughput, but they would include the platter rotation speed, which is measured in revolutions per minute, or an RPM value. And for most laptops, you would likely encounter 5400, and for most desktops, it would be 7200, but there are some models that go as high as 10,000 and even 15,000, but they would not be nearly as common. Internal cache is a small amount of built-in memory, just like your system memory, which is much faster than a spinning disk, that can be used to temporarily store data while certain operations are occurring. For example, if a very large file has to be retrieved from the disk, it will do so in many small read operations, so as each chunk of data is read, it can be placed into the cache until the entire file is ready. Likewise, for very large write operations, all data can be written to the cache first, so that as far as your application is concerned, once it's in the cache, the application can consider the write operation to be complete, and it can move on to other operations. The cached data will then be written to the actual disk in the background, so a larger cache can simply store more data temporarily and allow the disk to handle those large operations more efficiently, but the amount of cache will vary depending on the manufacturer, make, and model. And as mentioned, there are different interface types, but these days serial ATA is certainly the most common, which would outperform most other interfaces, including all implementations of IDE and all but the fastest revision of SCSI, which again is likely only going to be found in network servers. Now, regardless of those performance specifications, in a direct comparison to solid-state drives, in virtually every case, a magnetic hard disk drive will underperform a solid-state drive. It's just a completely different type of technology, and most notably, in a solid-state drive, there are no moving parts. So even the best performing magnetic hard drive simply can't compete with solid-state. But they do have higher capacity. So in many cases, they're still preferred when you need to store a very large amount of data, such as backups or archived files. And for those types of storage, speed usually isn't as much of a concern because the data, although it needs to be retained, usually isn't accessed very often. So in some cases, capacity is more desirable than performance. When it comes to the physical size, for desktop computers, you will almost always find a 3.5-inch drive, which refers to its width. And in most cases, there are one or more bays that are easily accessible within the computer once the cover is removed, with access to mounting screws on either side. So they're quite easy to install and or remove. And if you're looking to upgrade your system, adding a hard drive is a very cost-effective way to increase your capacity as long as there is an available bay and as long as you have an available interface on your motherboard, which, by the way, would be likely if your system supports serial ATA. On many motherboards, there may be up to 4 serial ATA interfaces built in, but even if there was only one, which would be unlikely, you could also purchase a controller card that installs into one of your expansion slots, which would then have many serial ATA interfaces. By contrast, the 2.5-inch form factor is not only an inch narrower, but it also tends to be significantly thinner. Hence, these are much more commonly used in laptops, where space is the main concern. That said, you can use the 2.5-inch drive in a desktop, but you would need an adapting mounting bracket for it to fit into the larger drive bay. Now, everything is a little more tightly packed in the 2.5-inch drive, if you will. As such, they tend to have lower capacity than their 3.5-inch counterparts within the same price range, and they tend to spin at 5,400 RPMs, so the transfer rates aren't as high either. But because of that, they tend to produce a little less heat and a little less noise, both of which would typically be desirable in a laptop. Finally, it is worth mentioning the hybrid drive, which, as its name indicates, is a combination of both a traditional hard disk drive and a solid-state drive in a single unit. Now, these came about primarily when solid-state drives were new on the market, so they provided an option to upgrade incrementally, for lack of a better word. But in terms of functionality, most of the frequently accessed data, such as the operating system itself and the applications that were installed, were stored in the solid-state portion, which provided for greater speed when booting and launching applications. Then the less frequently accessed data, such as personal files, would be stored on the traditional magnetic disk, where there was greater capacity. So, in short, you got the performance of solid state, for the most part, with the capacity of a traditional hard disk drive. At the time, they would have been somewhere in between with respect to cost, but the overall cost of purely solid-state drives has now come down significantly, so I doubt that you'll see many hybrid drives in use today. All told, when it comes to storage these days, solid-state is certainly the better option for performance, but when all you need is high-capacity storage for infrequently accessed data, traditional hard drives would be the better choice. In this video, we'll examine solid-state drives, or SSDs, which are rapidly becoming the successor to traditional magnetic hard drives as the primary means of storage for computing devices, most notably because although solid-state drives implement essentially the same type of memory as the RAM in your computer, there is one distinction in that where RAM is volatile, meaning that it requires power to retain data, the memory used in solid-state drives is non-volatile, meaning it does not require power to retain its data, just like traditional hard drives. Now, this isn't exactly new as a technology. We've been using devices such as flash drives for decades, but quite simply, it was an expensive technology. So, the cost to implement enough non-volatile or static memory in a device to provide a similar amount of storage to a hard drive has only recently come down enough to make it a feasible choice, and even today, solid-state drives would still be reasonably more expensive than their hard drive counterparts, and they typically still do not provide as much capacity. But that said, because it is just static memory, solid-state drives have no moving parts, whereas of course a traditional hard drive has a spinning disk and a moving actuator arm. So solid-state drives offer a significant performance boost over hard drive, particularly during the boot process and when transferring very large files. Just to give you a general idea of that, the last system that I owned that had a traditional hard drive used to take about 2 minutes to fully boot into the interface of the operating system. The laptop that I'm using right now, with the solid-state drive, fully boots in about 12 to 15 seconds. And even that's probably a little slow compared to the newest systems on the market. In addition, because there are no moving parts, solid-state drives are also less prone to wear and tear. For example, if a laptop with a traditional hard drive were to be dropped, the laptop itself might survive, but the shock might damage the moving components of the hard drive. In fact, the reason we say to this day that our system crashed when it fails is because the read-write head of a traditional hard drive hovers very slightly above the surface of the platter. So crashing referred to an instance where that head actually came into contact with the platter, which could cause significant damage to either the platter or the read-write head, to the point where it might need to be replaced. So with no moving parts, that simply can't happen in a solid-state drive, so they tend to be more durable over time. Now, I'd like to qualify that statement in that this refers to physical damage. I'll be covering some of the disadvantages of solid-state drives shortly, and we'll talk about some situations when they might not have a lifespan that is as long as traditional hard drives, but that refers to the longevity of data storage. But I'll clarify that more in a moment. But these days, particularly when purchasing a new computer, we're looking for performance, and in that regard, solid-state drives significantly outperform traditional hard drives in virtually every aspect, including reading and writing the data, booting the computer, launching applications, and transferring files, because the data need only be retrieved from specific addresses in the drive. There is no disk that has to spin to the correct location, nor an actuator arm that must be placed over the correct sector of the disk. Other advantages include no requirement for defragmentation of the data on the drive. Now, for those who may not have worked much with traditional hard drives, due to the nature of a spinning disk, the fastest access is around its outside edge. So data will initially be written as close to that outside edge as possible, but ultimately that space is going to fill up. So data will then be written more toward the center as space becomes more limited. Plus, for all the data that is stored on the disk, it's broken up into very small units known as clusters or allocation units. You may also hear the term sector, but that's more of a physical division on the disk itself, as opposed to a logical division of a file. Regardless, over time, files get written, edited, moved, copied, deleted, installed, and uninstalled. So you can simply end up with fragments of the file in many places on the disk, some possibly close to the edge, others toward the center. So to access a file that has many fragments in many locations, it will of course take more time. Now, you could defragment the drive, which effectively reordered everything so that all clusters of a file were at least all very close to each other. But this was really an ongoing and never-ending maintenance issue, particularly if your drive was very low on space. But with solid-state drives, fragments are simply stored in logical addresses in the memory, and one address is really no different than any other because, again, there's no spinning disk. The system need only know what the address is, so fragmentation becomes virtually irrelevant. The lack of moving parts also results in very little, if any, operating noise. Because it is just a collection of memory circuits, they are almost all physically smaller than hard drives, and again, because they don't require any kind of motor to spin the disk or move an actuator arm, they draw less power. But there are still some limitations. On a per gigabyte basis, they're still more expensive than traditional hard drives, and they also tend to have significantly lower capacity than hard drives. Which is not to suggest that you won't be able to find one large enough to suit your needs, but the higher capacity, of course, the higher the cost. For most systems these days, the internal solid-state drive is usually more than adequate to store the operating system, the applications, and for most people, all of the data. But given how relatively inexpensive external storage has become, for those who do require more storage, external devices can provide as much as you need, so the performance gains of solid-state drives will usually outweigh any capacity concerns. Traditional hard drives, however, usually had built-in monitoring capabilities. For example, if it was having difficulty accessing data in a particular area of the disk, it would actually report that and mark that section as unavailable for future use, so you would effectively know the status of your drive. And that doesn't really happen with most solid-state drives, but that said, those bad sections of the disk usually arose due to the wear and tear associated with the moving parts of a hard drive, which again are simply not present in solid-state drives. Now, this is the disadvantage I said I would come back to, in that solid-state drives can have a shorter life cycle than hard disk drives with respect to how long data can be reliably stored. Now, in most cases, you'll likely upgrade the computer or the device before deteriorated data becomes an issue. But because solid-state drives are just tightly packed memory circuits, they can run hotter than hard drives. So over time, they're still subject to wear and tear just like traditional hard drives. So if long-term, reliable data storage is what you're looking for, traditional hard drives might be a better choice. Plus, if it's the case whereby that data is not going to be accessed very frequently, such as a data archive, then the higher capacity and lower cost of hard drives would actually be more desirable in that case. So, in short, solid-state drives are better suited to storing less data that is accessed more frequently over shorter periods. Hard drives would be better suited for a large amount of data that is being archived over very long periods and very infrequently accessed. Now, like traditional hard drives, solid-state drives also have a few different interface types, including non-volatile memory express, or NVMe, peripheral component interconnect express, or PCIe, and serial ATA, or SATA. NVMe was designed with solid-state drives in mind, and it implements faster input-output operations than those of earlier storage interfaces, and it's independent of the form factor of the drive itself, so NVMe is becoming the standard for both network servers and client devices such as desktops, laptops, and other devices such as gaming consoles. But NVMe is more of a communications protocol that actually runs on top of an interface such as PCIe. But as an interface, PCIe also supports many other types of devices, such as graphics cards, Ethernet cards, RAID controller cards, and many others. So, in short, NVMe, as a protocol, can operate over interfaces other than PCIe, and PCIe can support devices other than solid-state drives. But for many of the internal solid-state drives of today's devices, you would most likely find NVMe over PCIe. Now, serial ATA is certainly still available, but largely for backward compatibility. If, for example, you were looking to replace an existing magnetic hard drive with a solid-state drive, the existing interface of your computer would very likely be serial ATA. But with respect to solid-state drives, the serial ATA interface would most certainly be a bottleneck in terms of performance compared to NVMe over PCIe. There would be several factors to consider, but overall, or at least on average, you could likely expect NVMe over PCIe to be about 4 to 5 times faster than serial ATA. But of course, if compatibility is the more important factor, then serial ATA might be the better choice. Finally, the form factor refers to the actual physical size and shape of the device, and for lack of a better word, the standard or internal solid-state drive that you would likely find in something like a laptop or a desktop is simply known by its size of 2.5 inches, which refers to its width. Now, that's the same size as a traditional hard drive that you would find in a laptop. But there are two primary others known as M-SATA and M.2, which is usually just referred to as M2. M-SATA stands for Mini Serial ATA or Mini SATA, and it's physically smaller than the 2.5 inch, most notably in its thickness, in that most M-SATA devices would only be about as thick as any expansion card. In other words, they're a little more than the circuit board itself, but that kind of size makes them ideal for smaller notebooks or laptops. But while M-SATA often physically installs into a PCI interface, it still uses the serial ATA protocols, so it isn't as fast. The M2 form factor is smaller still, typically resembling a RAM chip in terms of size, so it's ideal for tablets or other very mobile devices, but it was designed specifically for the PCI interface, which offers better speed, so M2 is effectively becoming the replacement for the M-SATA standard. In this video, we'll take a look at implementing what's known as RAID, which is a hard drive configuration that stands for Redundant Array of Independent Disks. Now, this is something that allows you to store data in a redundant manner, but despite the fact that the R stands for redundant, there actually is a non-redundant implementation as well, but we'll come to that in just a moment. Now, the primary reason for implementing RAID is for reliable data storage. Now, that said, all implementations of RAID use multiple hard drives to store the same amount of data, hence the A of array. So this introduces a potential vulnerability because what can happen if you are using multiple hard drives is that you are a little more likely to lose any one of those hard drives due to failure. So it implements the redundancy to be able to recover from that failed drive. Now, we'll get into that in a little more detail very shortly as well, but this is a relatively low-cost solution that is more commonly implemented in network servers where the reliability of data storage is more important, but you could implement it on a desktop system as well if you wanted to. Now, before we get into the specifics, there are two primary categories of RAID, one being what's referred to as software-based and one being referred to as hardware-based. Now, for either situation, you do have to have multiple hard drives. So in that regard, the hardware that we're talking about here really doesn't refer to the drives themselves, rather how the overall solution is managed. So a software-based RAID implementation simply means that you don't have to purchase anything extra as long as you have multiple hard drives already present in your system. You could use the inherent software of the operating system to configure a RAID solution. So in this graphic, we're actually seeing an example of the disk management utility on a Windows-based system that does have multiple hard drives installed. So with that, you could simply select those multiple drives and use this inherent software to configure a RAID solution, and the operating system itself will manage the overall solution. But hardware-based RAID means that you go out and you purchase what's known as a RAID controller card. This card gets installed into one of your expansion slots and likely comes with vendor-supplied software as well. So you don't have to use something like the inherent disk management utility of Windows to configure the RAID solution. Now, typically hardware-based is preferred because the controller card, for starters, would likely give you access to more physical hard drives than what your motherboard might support natively, and typically the controller cards themselves also tend to have a very large memory cache installed. So when you're performing very large operations such as writing a lot of information to the RAID array, it can store that information on the cache, then write it to the drives after the fact. So as far as your application is concerned, once it's in the cache, it can consider that data to be fully written and it can move on to other operations. So again, hardware-based typically is better in terms of performance, but of course you have to go out and purchase the RAID controller card, so it could be a little more expensive, but typically these days the cost wouldn't be all that high. Now, with respect to what RAID is all about, there are several different levels that we'll take a look at here, and in fact there are more than what we'll see, but these are the most commonly implemented. So RAID 0 is referred to as striping, and this is the configuration that in fact does not have any redundancy, hence the 0. So striping is typically implemented for performance, and we'll come to that in a moment as well. But in terms of implementation, in this example, we only have 2 disks, and I do want to point out that you could have many more than just 2, but 2 is sufficient to implement striping. So let's just imagine a single file being written. What it will do is break it down into multiple blocks. Now, there's 8 blocks in this example, but the number of blocks is simply dependent on the size of the file. Generally, each block is maybe around 64 kilobytes, but that might also vary depending on the software and or the hardware solution being used. Anyway, as many blocks as are needed are created to store the entire file, but then the blocks are written across both disks of the array. So in short, in this example, 50% of the file is on disk 1 and 50% of the file is on disk 2. Now, in terms of the performance benefit that I mentioned a moment ago, this does perform better because particularly when you are reading the file, you can read from both disks at the same time. Even when writing, you can also write to both disks at the same time, and recall that if you have a hardware-based solution, the cache on the controller card can greatly speed up these operations as well. And, as I mentioned, you can have many more than 2 disks. In a lot of RAID solutions, in fact, you can have up to 32. So the more disks you have, the better the performance. But the downside, again, is that there is no redundancy in a RAID 0 implementation. So if you do have, let's just say, 10 disks, well, you are 10 times as likely to lose any one disk. So with a RAID 0 solution, the only benefit really is performance. Since there's no redundancy, if you do lose even one of those 10 drives, then you have to restore the data from a backup. So the next level is RAID 1, which is referred to as mirroring, and this does implement redundancy because effectively you get an identical copy of every file written to any given disk. So here we see block 1, block 2, block 3, block 4 on disk 1, and we see the exact same blocks on disk 2. Now, this configuration can still give you a bit of a performance boost on the read side because you can read from both disks at the same time, but on the write side it's going to be slower because you have to write twice as much data. Now, you can still do that simultaneously, but it requires more processing to do that. So RAID 1 is typically not really implemented for its speed, rather for its redundancy, because if you lose either disk, you're fine. You have a complete and identical copy on the other disk. Now, I should also point out that for RAID 1, as the name indicates, mirroring is only ever configured on 2 and only 2 disks. You could create more than one mirror set in any given computer, but any single RAID 1 array uses 2 and only 2 disks. Now, that said, there is one caveat to that, in that these days there is also a configuration known as three-way mirroring, which of course would require more than just 2 disks, but that is officially not a RAID 1 array. You'll typically hear it referred to as a RAID 1E array for enhanced, or some people might simply say it's a three-way mirror. But again, for an official RAID 1 array using just two-way mirroring, it's always 2 disks. Now, RAID 5 is referred to as striping with parity, so it still uses the same striping that we saw in RAID 0, but recall that striping on its own does not provide any redundancy. So this is where the parity comes in. Now, you do have to have at least 3 disks for a RAID 5 array, but again, you can have, in most cases, up to 32. But if we look at any given file, again, it's still broken down into blocks. So we see block A1, A2, and A3. So that would represent a single file. Then we see parity information for that file. So parity A is for blocks A1, A2, and A3. Then we see the same thing for blocks B and C and D. So with respect to what the parity itself is, let's just go with one example. Block A1, block A2, and block A3 would represent the file as a whole, but then the parity would be some kind of a mathematical calculation that can be used to recalculate any missing data. Now, this is a very simplistic example, but imagine that block A1 is represented by the number 1, and that block A2 is the number 2, and block A3 is the number 3. So in terms of a mathematical calculation, what you can do is to simply add those up. So 1 plus 2 plus 3 equals 6. So parity A would equal 6. This way, if you lose drive number 2, you can simply perform that same calculation in reverse, if you will. 6 minus 3 minus 1 equals 2. So you now know that block A2 had to contain the number 2. So you can regenerate that data. So imagine the disk entirely failed. You simply get rid of it and you install a new disk. Since there's parity for all blocks and all files, you can simply install a new hard drive. Then the system will regenerate what used to be on that disk by using the surviving disks and the parity information. So since the blocks and the parity are all spread across all disks, it doesn't matter which disk you lose, as long as it's only one disk. And I do want to point that out. Parity can only recover from a single disk failure. If you were to lose 2 disks, then there's not enough information left to be able to determine what the missing data is. But the chance of losing 2 disks at the same time, of course, would be much lower than just losing a single disk. Finally, RAID 1 plus 0 is a stripe of mirrors. Now, this is also very commonly referred to as RAID 10 because of the 1 plus 0. But as mentioned, recall that RAID 0, striping all by itself, does not provide redundancy, but it does provide very good performance. So RAID 1 is then implemented on top of this, if you will, which uses mirroring, which does provide redundancy. So what we have is striping of blocks A1 and A2, in this case across disk 1 and disk 3, so that's the striping characteristic. But we then have another disk mirroring each of those. So again, what you would have is that as you are reading and writing data, you would just be working with one set of disks. So again, let's just go with the A block. I would read the file from disk 1 and disk 3, but as any information is written, of course, it would be written to all of the disks so that if either of them is lost, we still have a complete and redundant copy of that information. So now we get the performance benefit of striping with the redundancy benefits of mirroring. And in fact, I should also point out that when you use RAID 1 plus 0, You can, in fact, survive the loss of two disks, because if I were to lose, let's say, disk 1 and disk 3, I have identical copies of both of those. The same holds for if I were to lose disk 2 and disk 4, or disks 2 and 3, or 1 and 4, because again, there are identical copies of each of those. So RAID 1 plus 0, in fact, provides the highest level of redundancy. Now, that said, this would be the most expensive implementation because for what would normally just be a 2-disk striped array, we now need 4 disks. So it costs twice as much in terms of the number of disks, but again, it's very high performing and it gives you redundancy. Now, with respect to which implementation of RAID you should go with, it typically comes down to your needs. If you just need redundancy, then usually RAID 1 or mirroring is fine. If you just need performance, then usually RAID 0 is fine, but recall that you would need backups. So then RAID 5 or 1 plus 0 would give you both, but then it might come down to the cost and or the complexity of the configuration. But again, these days, the cost of hard drives is not particularly high, nor is the cost of a controller card. So I would say that you could implement a fairly robust RAID solution for probably well under $1,000 maybe at the time of this recording, and I would estimate that would get you the controller card and at least 5 hard drives. So again, the configuration is up to you, and it will always depend on the implementation, but RAID is a very good option for ensuring that you can recover from the failure of a drive without having to resort to backups. Now, one final point on that note, even if you do implement RAID, I still would never suggest that you should go without backups. Okay, you should always have backups, but at least with a RAID solution, you might not need those backups as often. In our final video for this course, we'll take a look at several types of removable storage, beginning with flash drives, which use a type of memory known as electronically erasable programmable read-only memory, or EEPROM, which simply means that the data stored in the memory can be written, erased, and rewritten many times. But it also has the characteristic of being non-volatile, which means power is not required for data to be retained. Because flash drives are just a collection of memory chips, they offer very fast access times, and due to their small size and light weight, they're quite shock resistant and durable, and even if damaged or lost, it doesn't cost very much to replace them. Key uses include short-term data storage, which is not to suggest that data can't remain on flash drives for long periods, but given their portability, they're simply easy to lose or be left behind, so they shouldn't be relied upon for applications such as backing up important data. But because they're so small and portable, they're ideal for bringing large amounts of data with you. For example, when I first began in IT, the only real portable storage device was the 3.5-inch floppy disk, which could only hold 1.44 megabytes of data, not even enough to store a single high-resolution photograph of today. Modern flash drives can easily accommodate 32, 64, or even 128 gigabytes. In some systems, they can be used for RAM enhancement. You can quite literally insert the flash drive and configure the operating system to use it as additional RAM if the system is low or simply doesn't have enough installed. And in some cases, they can even have operating systems installed, which can be used to configure a multi-boot system as long as your system supports booting from the USB device. Common types of flash devices include the USB flash drive, which is also commonly referred to as a memory stick or a thumb drive. Compact flash, which is generally implemented as a small card, which are often found in digital cameras, which also applies to the secure digital or SD card, which also comes in different sizes, the mini SD and the micro SD, for even smaller devices such as cell phones, media players, or GPS devices, and an older specification known as the XD picture card, found only in cameras, as the name would suggest, but this format has largely been superseded by newer formats such as the SD card. Next is the compact disc storage medium, which was released in the early 1980s as a portable storage medium for data, audio, and video, but at the time it was primarily a read-only mechanism, hence the term CD-ROM, whereby the ROM stands for read-only memory. As an example, you might have purchased music or perhaps software on a CD, but you could not write any information back onto that disk. This did become common afterward, but most of us did not have CD burners at the time that CDs were introduced. Now, you may also hear CDs referred to as optical storage because they're written to and read from using a laser that reflects off the surface as opposed to an electromagnetic charge. And because of their physical size and the accuracy of a laser, they offered far more storage than their floppy disk counterparts, in most cases up to 650 to 700 megabytes compared to the 1.44 megabytes on a standard 3.5-inch floppy disk. So this of course was a tremendous improvement for portable data. However, while the duration of how long data could be reliably stored on the disk could be measured in decades, that was entirely dependent on how well you cared for the disk, because they were quite prone to damage if not carefully placed into their protective case after each use. The surface could be easily scratched, which could render the disk unusable. So as mentioned, in their original iteration, most CDs were read-only. So regardless of whether you did have a CD burner, a read-only disk itself simply did not support writing any new data. Hence the CD-R, or recordable, was introduced, which was essentially a blank disk that allowed us to write our own data. But CD-R used what was known as write once, read many technology, meaning that you could only write data one time, after which it was read-only. To address that shortcoming, the rewritable allowed for exactly as its name promises. Data could be written, but then overwritten if need be. The CD-ROM extended architecture just allowed for multiple different types of data to be written, for instance audio, video, and data all on the same disk. And there was also a specific CD for video, or CDV, which was typically implemented along with the MPEG file format. It had higher resolution support and allowed the video to be stored in an uncompressed state, but still with the capacity of only 650 to 700 megabytes in total, this didn't allow for very much video, really only a few minutes in its uncompressed state, so things such as home videos could be stored, but certainly nothing like an entire full-length feature film. Now, just quickly, this is where the device known as the CD burner came into play. So, in order to be able to write to any format, your device had to be a burner. But most early devices were players only, so a lot of upgrading had to be done around this time. Burners quickly became standard in newer systems, but they also required specific software to be installed to allow you to write data. And the term burning, by the way, draws from the fact that in the original writing process, before rewritable disks, the laser quite literally burned a small pit into the surface of the disk, which meant that as light bounced off the surface when reading, it would interpret the non-pitted areas versus the pitted areas as ones and zeros, because the light took different time intervals to reflect back to the reader. In the rewritable iterations, the laser used more precisely controlled temperature variations to interact with the chemical composition of the disk, altering it from one state to another, each state representing a 1 or a 0. But because it did not burn an actual pit into the surface, this change of state allowed them to be rewritable, because you could change the state from one state to another and then back again. Despite the tremendous advance in storage capacity of CDs, the digital versatile disc, or DVD, was the optical storage successor to CDs. Introduced in 1995, by which time CDs, like their floppy disk predecessors, were regarded as not having enough space anymore for the current removable storage requirements. In its initial release, DVDs supported up to 4.7 gigabytes, over 7 times more than a standard CD, and by their final iteration, a single DVD supported over 17 gigabytes in what's known as a double-layer, double-sided disc, whereby the lasers could read from both the top and bottom surfaces, and different chemical compositions were used to define distinct layers on each surface, so the laser simply altered its intensity to reach the deeper layers. Now, I should also just quickly mention that DVD does in fact stand for Digital Versatile Disc, and I'm pointing this out because you may still hear them referenced even today as digital video discs, because one of their early implementations was to store feature-length films. Those of you who remember going to video stores may have often heard that term, but they can in fact store many types of common data, including video, audio, and standard documents, hence the term versatile. But as mentioned, movies were certainly a very common implementation, as was gaming, effectively because they had such higher capacity than their CD predecessors. In terms of features, apart from movies or games that were pre-written to the DVD, they were introduced with write and rewritable capabilities. However, like CDs, you needed a specific burner for DVDs because it's an entirely different format, so once again, a lot of upgrading occurred. Particularly for anyone who may have been a little late in purchasing a CD burner, it wasn't all that long before a DVD burner would have been required. But at least you didn't need to have both. Most, if not all, DVD burners were at least backward compatible with CDs, and they could read or write for both formats. Now, some of you may be familiar with HD DVD, which refers to high definition, but in order to accommodate high definition resolution, in fact, it has to specifically be an HD DVD. A regular DVD, for lack of a better word, did not support high definition video. And while everything associated with DVDs would have been more expensive than CDs, by today's standards they would in fact be quite inexpensive and cheaper still than their successor, Blu-ray, which we'll see in just a moment. But in terms of their physical specifications, they were exactly the same size as CDs, hence part of the reason why a DVD burner is backward compatible with CDs. So, as mentioned, Blu-ray discs appeared as the successor to DVDs, and their name is drawn from the fact that the laser being used is actually blue, which has a shorter wavelength than red, which is what was used with CDs and DVDs. So that shorter wavelength allows it to be more tightly focused, and once again, this translates into increasing the capacity over DVDs. In a double-layered format, a single Blu-ray disc supports up to 50 gigabytes, providing support for high-definition and even ultra-high-definition content, making it an ideal format for movies and video games. Once again, though, for all those who bought DVD burners, more upgrading was required, but the disc itself was still the exact same size as both predecessors, so most Blu-ray players also include a red laser, making them backward compatible with DVDs and CDs, but that would be dependent on the manufacturer. And if it is just a player, in other words, not a burner, then of course you can read from all, but you can't write to any formats. But of course there are Blu-ray burners as well, but many of us likely have a Blu-ray player only in our entertainment centers right now. But on the topic of burning, if you do have one, the standard capacity of a single layered disc is up to 25 gigabytes, which even in its initial format improves upon the maximum capacity of DVD, but Blu-ray only implements additional layers as opposed to multi-sided discs. So a dual layer supports up to 50 gigabytes, then the XL or extra large version 3 supports up to 100, and the XL version 4 up to 128 gigabytes. Now I should mention that these values represent the total overall capacity, including some reserved space for file management and error correction, so the practical values would be a little bit lower, and the deeper the laser has to penetrate, the less reliable it becomes, so XL versions 3 and 4 aren't as commonly seen in standard applications. Regardless, removable storage has unquestionably come a very long way since I began my career, with capacity levels and speeds that were simply unimaginable at the time. I reiterate, the 3.5-inch floppy disk was the standard for removable storage when I started, and it stored 1.44 megabytes. Even just a single layer Blu-ray disc stores 25 gigabytes. That's the equivalent of over 17,000 floppy disks. Four and 5, and error checking and correcting RAM, single, dual, triple, and quad channel memory, hard disk drive and solid-state drive storage solutions, and redundant array of independent disks or RAID levels 0, 1, 5, and 10 configurations, and removable storage. In our next course, we'll move on to explore how to recognize, install, and configure motherboards, central processing units, and add-on cards.